Hello, hello, and welcome to episode number 178. Can't believe it's already 178 episodes. Seems like, it definitely speaks to the fact that I've been here for a bit, and it's really been pretty amazing. Like, um, yeah, pretty wild. If you're out there, let me know in the chat. It'd be awesome to see who's with me. Today, we are going to be doing a bit of a deep dive into service type load balancer. We're going to be talking about different things, going through different configuration parameters, showing how to troubleshoot things, etc. Should be a lot of fun. I hope you're tuned in, and I hope this is interesting for some of you, but for me, it should be a lot of fun. Let me get my screen shared here. All right, first up, we have the news. Of course, if you go to cilium.io/newsletter, you can sign up for the news yourself without any challenge whatsoever. The most recent one is put up by our good friend Bill, who put it up on the 8th of April, just before tax day here in the US. Another KubeCon in the books. He's been at this for 20 KubeCons. I'm like, my goodness, I think I'm like in the 15s or 16s or something somewhere. It's the biggest one yet, and I do agree. I think it was like 13,000, 12,500 people, something like that. It was an amazingly large space in London. It was pretty wild. But we've just done a wrap up in the previous episode, so I'm not going to jump into that. If you'd like to see some thoughts about the close of KubeCon in London, go ahead and check that out. Hey, Joseph, good to see you. Welcome. And welcome, Genetek. Good to see you both. The technical, what if CI/CDs had built-in security and observability, adding eBPF to GitHub Actions with code on GitHub? That looks pretty cool. So we're running eBPF inside, and then what are they doing with the actual action? Hard to see, actually. I can see the mounting of everything. Must be this eBPF GH action here, but it doesn't say like what it's actually doing inside. Pretty neat, though. I mean, you could run the Tetragon agent, I guess, in that way. And you'd have a lot more information about what was happening inside that. If you ran it that way, I think that's a pretty cool use. There's a bunch of other interesting stuff out there. Exposing apps and Kubernetes from services to gateway API. It's pretty relevant to our talk. We're going to be kind of leveraging a bit more of the services side of things, but there's definitely some cool stuff happening with gateway API as well. Kubernetes networking, eBPF in action, IP blocking with XDP, which is very cool because if you leverage XDP to do IP blocking, it basically kills it right there at the network interface. It means it never actually uses any CPU cycles on the machine that you're using to actually interact with that packet, because you've dropped that packet before it even shows up in the stack. Pretty amazing when you think about it. And then we can do that with what we get. The benefit that Cilium gets out of XDP is that it can actually be kind of the point where we pick up the packet and short circuit it. So instead of actually having to send that packet all the way through all the things, we can just take it from XDP and send it directly to the socket that the application is running on. If you think about it, that greatly short circuits, so it reduces the number of times it has to go back and forth between the user and kernel space, and can be pretty awesome for performance. Oh, nice. Nico put up a repo that has a list of all of the Cilium weekly videos. Definitely check those out. They're pretty awesome. The eBPF verifier visualizer. That looks pretty interesting. I'm not going to jump down that rabbit hole at this moment because we have a lot to cover today, but there's a lot of stuff, a lot of really great stuff here in the newsletter. And as I said, you could definitely check it out by going to cilium.io/newsletter. eBPF swag store is open. Pretty cool. Get your eBPF logos. Camouflage eBPF. That's hilarious. Yeah, good stuff. So let's jump into it here. Oh, before I jump into it, I did want to share this article that I've seen, that I came across today in the technical side of things. That absolutely blew my mind. It's this guy, Jean-Francois Nadeau in France. Apparently, he wrote this. He put this up in February 20th, and I just came across it recently. Now, to set the stage, this article is about leveraging pretty much any Kubernetes CNI in EKS where you want to leverage overlay mode. And doing that represents a couple of different challenges. First of all, like to be able to use overlay mode in EKS or any other environment, right? Oh, well, let's keep it to EKS. I think that's more relevant. So to leverage overlay and mode in EKS, what ends up happening is that you kind of break the networking model that AWS has for its Kubernetes services. Because if you leverage like Cilium's ENI mode, or if you leverage the AWS CNI, what it does is it actually puts all of the pods on the same networking in the same VPC as the API server, as the nodes themselves, all of those things. Now, there's things you can do to separate them, right? Like, so for example, you can use a secondary CIDR for the pods and a different CIDR for the nodes, etc. There's lots of ways to tune this, but fundamentally they are still routable and they're still right there in the same layer. And the benefit of that is that, like in AWS, if you want to register an admission control webhook and make use of, say, the ALB or the Amazon Load Balancer or application load balancer inside of your Kubernetes environment, then the ALB actually has an admission controller, a webhook that has to be registered with the API server, and that kind of creates sort of this chicken and egg situation where if the pods themselves are not routable for the AWS server, for the AWS API server, if the API server can't reach the pod IP, and the only way that it can is if that pod IP is expressed on the VPC routing fabric, then it won't be able to actually make that webhook work. And you may, and some webhooks fail closed, which means that nothing will work. But that connection between the API server and the webhook pod is the interesting part of this article. Historically, what ends up happening is that most people, vast majority of people, leverage Cilium's ENI mode, right? Wherein we replace the AWS CNI, but we behave exactly the same way as the AWS CNI does, and in that way, we wire up the pods up to the VPC routing layer, and that means that any webhooks and everything just work, the ALP just works, all of that stuff just works. But what if you really did want to make use of overlay networking because you want to get rid of the requirement for how many pods you can run on a node? There's ways to combat that as well, but that's beside the point. Like, whatever reason is, you want to actually just use an overlay network for your pods. Like, you want to reuse that same CIDR. You don't want to necessarily put all of your pods on the routing fabric. What can you do instead? Now, to date, it's been a pretty tough thing to solve. Like, one of the ways to solve it is to make it so that the actual webhook pods are on the host network. But even that's a little challenging because how many of them can you put on the host network? What is the port, et cetera, et cetera. You can see how this gets a little bit complex. But this write-up introduces a new idea to solving this problem, which I have to say is probably one of the slickest one I've seen. And this leverages a native feature of AWS, which is the Gateway Load Balancer, the GLB. And the Gateway Load Balancer is a load balancer that does a pretty cool thing. It can be deployed into your Kubernetes, into your AWS environment, and then have a route pointed at it in the VPC layer. So in the VPC layer, let's say we could create a route for the pod network, and we could forward that route to the Gateway Load Balancer. Now, what is the Gateway Load Balancer going to do with it, right? That's the interesting part. The Gateway Load Balancer could then, leveraging Geneva encapsulation, forward that traffic to some target. And that target could be a pod running inside of the pod network, right? So if you have that pod and you have like the host port expressing it so that when traffic lands on on a node. It gets sent into that pod. That pod then decapsulates the Geneva traffic and then forwards that traffic to the destination pod IP. So that's actually pretty clever, because what that does is it makes it so that the pod network that in the overlay network, right, the pod CIDR that is part of the overlay network that is not expressed in the VPC can be, right? You can add a route in the VPC routing layer that says, for the pod network, I want you to forward all traffic to this gateway load balancer. And in the gateway load balancer configuration, you say the target IP addresses for this will be the IP addresses for the nodes themselves inside of the EKS network. And when that traffic lands on the node, it will terminate. That traffic will be forwarded up via host port into the pod that will do the decapsulation of Geneva and then forwarding that traffic into the webhook. And the other interesting thing here is this last part of the article here, which is that really highlights the point that when the traffic shows up in the pod network, it looks like the source of that traffic is coming from the actual GLB tunnel handling program, right? Which is a pod with its own identity, which is part of the pod network. And when it terminates there, now we have a source identity that is unique to the type of traffic that would be coming necessarily from it. So we could actually even write network policy that says, I only want to allow traffic coming from this tunnel handler program to talk to webhook pods. It can't talk to other things. I'm not trying to express the pod network to other things within that gateway. It's very specific only to this AWS source. And honestly, the design of this is probably one of the slickest ones I've seen. I was really very impressed by this because it really solves a couple of the different design considerations I would have in this that are pretty important. One of them being like, isn't this a bottleneck? Aren't you kind of creating a challenge? And the answer to that is, while you are still transferring to a gateway, the backends of that gateway can be multiple, right? You can actually have, you could have a daemon set where all of this is running. You could have one pod per node and basically make it so that the entire cluster is the destination for this traffic, which is pretty cool. So yeah, I was super impressed. I don't know if you have this problem, but if you do, it's a fascinating solution to it. And it handles both directions, and it seems reasonably scalable, and it kind of leverages a way of solving this problem that I probably would never have thought of in a million years, but I was just super impressed by how this was solved here. All right, next one. Oh, and actually, yeah, that's another one, is that it actually makes use of the tunnel devices for this piece of it, because it has to use the decapsulation. I guess you can do that in Go, honestly. Probably don't need the tunnel device, but you get the idea. Very, very cool. All right, next up, let's talk about services. So this is a container lab environment that I brought up a while ago, and I was talking to you about before. I think make sure I have things up, which I do not, apparently. I'm going to do makeup. In a previous episode, I've gone through this configuration, but just to give you kind of a refresher, what this is it's actually just a environment that makes use of Container Lab, which is a way of creating like routers and that whole thing, and then actually associating interfaces from the lab routing layer with containers. So for example, I could use the lab control plane, lab worker 2, lab worker 3, and I can actually give them IP addresses on a virtual routing fabric, leveraging a separate interface, and then use that mechanism to basically interact with routers. So the benefit of this is that means that I can actually create more complex configurations. So in my case, what I'm doing here is I'm creating a 4-node cluster. I'm enabling BGP. I'm enabling peering between the Cilium nodes themselves and the BGP routers that I've created. And then I'm going to actually use that BGP implementation to announce things like service type load balancer. We're going to get into exactly how all of that works in this episode. But first, we're just going to go ahead and configure it, and then we'll kind of talk through the different configuration and how all of that works. But here's the configuration that really matters for us at the moment, which is right here, the BGP control plane enabled, L2 announcements enabled. These are two different features within Cilium that support announcing services of type load balancer. And we're going to get into like what that means and all of that stuff, and like how to use it and all of that here in just a minute. But I think that's actually pretty cool how that works. So now that that's all up, let's do a thing real quick and just kind of talk about what I mean by this. Right. So if I do kubectl explain service, so right here in the bottom of this section, it actually describes like the different types of service service. And to give you a high-level overview here, before we even get started with inside of Cilium, or sorry, before we're talking about Cilium at all, we're just talking about Kubernetes. In Kubernetes, there's four different types of service: cluster IP, external name, load balancer, and node port. And then there's also a service of type none, which is like a different thing, but we'll talk about that in a minute. The ones that we're really going to talk about in this context are cluster IP, external name, load balancer, and node port, and specifically cluster IP and load balancer. Now, in a bare metal world, like if I were just to bring up a kind cluster, and I created a service, and I tried to expose that service in a service of type load balancer, it would fail. And the reason it would fail is that the load balancer type of service inside of Kubernetes is usually implemented by some other system. So if you're in AWS, for example, and you have the cloud provider wired up inside of your Kubernetes environment, then when you create a service of type load balancer, a controller running inside of your cluster will determine that you've requested a load balancer, and based on some annotations and some other information for that service as it is defined, then it will go ahead and request a load balancer from the cloud provider and try to wire it up for you. But you can imagine that in a kind cluster or in most bare metal clusters, there's no such service. There's no such controller that does that for you. So how do you solve that problem, right? Like there's like, Kubernetes comes with like batteries that are not required but swappable kind of situation, right? Where like it defines the API, but it doesn't actually require that API is fulfilled. This is also true, by the way, of network policy, right? Like network policy is a defined Kubernetes API, but there's nothing requiring that all CNIs actually have the construct for network policy. So for example, in a kind cluster, stand that up, and you're leveraging kind net, which is the built-in one. This might have just recently changed actually, but for quite a long time, kind net had no idea how to implement network policy. So while you could still define it, it would not have any effect because there was nothing to implement the network policy component. This is kind of one of the interesting dimensions of Kubernetes is that there are a lot of APIs that are defined where we do the work of defining what that API means, but we don't necessarily give you any guidance on like what you should deploy that would fulfill it. Sometimes the docs make recommendations or give you ideas of different things that can be used, but there's nothing that like says you must, to be a Kubernetes cluster, you must have something that solves load balancers. That's kind of an exercise for the platform team or for the infrastructure engineering team that is involved. That said, we can do that, right? Cilium as a CNI does have the capability of satisfying services of type load balancer. That means that we will handle the wiring to make sure that when you create a service of type load balancer, this gets wired up and works. So let's go to the docs and take a look at how that works. And then we'll do some demonstrations and we'll jump into it here. So if I go to docs, I can spell So there's a couple different parts to it. I'm going to start with the BGP section. Actually, I mean, you could kind of see already from the Kubernetes networking service, networking section, like how some of this works. Service load balance. But that's still in kubeproxy installed on every node. And so service load balancing is another place where load balancing applies. And it's actually probably the most intrinsic one. So like one of the ways that service load balancing works, this is not talking about service type load balancer. This is talking about service type cluster IP, right? If I create a service of type cluster IP, then I'm also leveraging effectively a load balancer. Let's actually just look at that real quick, and then we'll come back to the docs. Let's create a deployment real quick. Let's do create deployment echo image equals inanimate echo server port equals 8080. Kubectl expose deployment echo type, and then I have choices. I can do a type of load balancer of cluster IP. If I don't specify anything, I create a service of type cluster IP. Right here, you can see right here in the type, I create a service of type cluster IP, and this cluster IP will then have a cluster IP of VIP, if you will, associated with it. And the way that that VIP works is pretty interesting, right? So now I have a service that's been defined. If I do kubectl get endpoints for that service, for echo, I can see that there's one pod on the back end of it. And so I see the front end, kubectl get services. I see the front end IP, 1096.202.47, and I can see the back ends are 10.1.3.1.15. And if I scale that up, let's say 2, we look at those endpoints, now we have 2. So this is effectively all that you need to understand that like this actually represents an internal load balancing mechanism within Kubernetes, right? Now the benefit is that other applications within Kubernetes can leverage this load balancer to talk to the Echo server. Now, because it's a cluster IP, only those applications within the cluster can do this, right? So if I were to create a bash service, you could overrun it, bash image equals bash bash. If I jump in here and I do a APK update, apparently I have a networking problem. Over. Oh, no, it worked. Right. No, it's not working. Is my problem DNS? It appears to be DNS. Let's see if that solves our problem. Our problem was DNS. We'll figure that out later. Anyway, so now that I've actually got that working again, I can do apk add curl. And then I can curl the echo service on port 8080. And you can see that this is actually sending me back to a particular node IP or a particular pod IP. My requesting IP, that's the IP address of my pod, which is 10.1.22.10.1.2.244, and then the host name of the pod, which is here. So let's just do grep host name, right? Let's SS. So that's host name, and if I keep doing this, you can see that I'm being load balanced across two different endpoints, right? And that is load balancing, leveraging Cilium, oddly enough. But let's talk about that. Let's talk about that a little bit more in just a second. So what's happening at the moment? What I've described is I've got a bash process running inside of the pod network. I've defined a service, and that service has a load balanced cluster IP. I can go ahead and hit that cluster IP, and what's going to happen on the back end is that somebody's making a load balancing decision and sending me to one or another pod, another healthy endpoint on the back end of that. And that's the cluster IP load balancer. That's true of every Kubernetes cluster. And the way that that typically works is by leveraging kubeproxy. But you can see in our case, there is no kubeproxy. I'm not running kubeproxy at all. So what's doing that work, right? And so in our case, this is actually being done this is being done by us, by kubeproxy replacement. So in our configuration, in this cluster, what's actually happening here is that the Cilium is making that load balancing decision. So when that cluster IP happens, and there is, let's see, Cilium, eBPF, LB, list. So here are all the load balancers that we know about, right? This is actually the load balancers programmed into eBPF that we know about inside of Cilium. And you can see that on the left here, we have the service network, or the service CIDR IP addresses. And on the right-hand side, we have IP addresses that are usually pods or just kind of announced or sending more generally to other things. If I do a grep for 8080, that is our service right there. That's the one we were just chatting with, right? 10.96.202.47. When I was interacting with eCHO from my bash service, it was resolving to this IP address and then sending that traffic back to one of these two healthy endpoints, depending on where that traffic was terminated. So here's Cilium already solving a load balancing mechanism. But let's talk about like some of the other interesting load balancing mechanisms within Kubernetes and how Cilium can address those as well. So back to doc. Now, the next thing I want to talk about here is going to be on this BGP side of things. So let's go here to the BGP side. And then inside of the BGP control plane, there's lots of docs here that really get into some pretty fascinating stuff. But what I want to jump into here is kind of like expressing services of type of load balancer. And that is in this documentation right here. So load balancer IPAM, load balancer IP address management is basically the way that we can define how Cilium will work, will actually support things inside of load balancer. Now, this is a higher order construct. This load balancer IPAM pool, this load balancer IP pool, you can create it, and there are some configurations that you can make that allow it to understand when to pull an IP address from this pool, but this is decoupled from the feature that will actually handle the load balancing. Load balancing can be handled by the Cilium BGP mechanisms, or it can be handled by the L2 announcement mechanism. And we have both of them wired up inside of this cluster, and we'll look at how both of them work as we proceed here. So in my cluster, I have BGP wired up and I have it configured. So let's take a look at how that's configured. So first let's take a look at the IP pool part of it. So let's do kubectl get Cilium load balancer IP pool. And we can see there are 3 of them, and there are IP addresses available across all of them, and none of them are currently conflicting. And if I do -o-YAML, and I look at the configuration for a given CIDR, so here is the load balancer for IP pool red. The CIDR that I'm announcing is 30.10.0/24, and that's the pool of IP addresses that I'll use for services of type red. And then the service selector here indicates what label should be associated with a service for this particular CIDR to be used to allocate an IP address for it. Now this is just wiring up the IP address for the service. So if I were to do kubectl get svc-a, so we can see already that one of the IP addresses has been used by the Cilium Gateway load balancer service inside of tenant red namespace, and that used the first available IP address that was configured. Now, what's interesting here is that, lost my train of thought, hold on, coming back. So this is actually how the IP address is configured. But nothing in this configuration necessarily, or in this view, tells me what backs that service, right? So if I were to go ahead and edit that service, let's see what other information we see here, right? So we can see that it's actually associated with the gateway API gateway. You can see external and internal traffic policy are set to cluster. You can see it's a service of type load balancer. You can see further down that the service is that's the IP address, and that the IP mode is VIP, and that Cilium satisfied that request. Now, what's challenging here is we don't know what is announcing 30.0.10.0. I mean, so let's take a look at how that might be done. So let's do kubectl get Cilium BGP peering policies. So this is one way to do this. In my case, it's actually the mechanism that I'm using to announce the services of type load balancer. But here's how this is going to work. So this is just one way to do it. You can also do this with like the newer API, and I have examples of that newer API as well. But just for the older API version of it, the way this works is that you can actually have node selectors that indicate which nodes that you're going to be defining here in this peering policy. In my case, I've actually labeled the nodes rack 0, rack 1, rack 0, and rack 1. And then I have 2 nodes in each rack. And just further down here, I've defined a virtual router. I'm saying don't export the pod CIDR. I don't want to announce the pod CIDR. What I want to announce is actually services of type load balancer. And specifically, I want to match only those services that have the following values in them: blue, red, and yellow. So don't announce any services other than ones that match that particular scheme. They have to be color in blue, red, or yellow, or I don't want you to announce them. And the same thing for rack 1. Announce those load balancer IP addresses, and only those ones that match this particular filter. Now, the benefit of this is that I can actually use different types of things to announce different mechanisms depending on what we're trying to do. So I can curl 30.0, 10.0, and I can actually see a response, right? If I go back to my browser, I can even navigate to that website because I've got myself configured as part of all of those networks. So if I do 30.0, 10.0, I can see the service that is exposed inside of my cluster on that IP. Which is pretty cool. So let's just expose the echo service in that way. Right? So let's do kubectl expose deployment echo type load balancer. Now, what's interesting is I've already got a service called echo, and if I just set the type, it's going to assume the same name. So if I hit enter here, it's going to error out because the echo service already exists. But what we want to do is we want to go ahead and create a service of type load balancer. Now we have two options. I could edit the service that's there and make it a type load balancer, or I can go ahead and make a new service that is type load balancer, and we can compare the two. So let's do that second thing. So now I've created two services. I can do kubectl get svc. We can see echo, and we can see echo lb. We can see that what's interesting here is that cluster IP exists and load balancer IP exists. Oh, but it's still pending. Now, if I were to go ahead and label the service echo lb color equals red, what IP address do you think it will get based on what we've talked about so far? Usually what it's going to get a 30 IP address. Let's take a look. All right, got the next available 30.0.10.1. And that was important that I labeled the service that way so that the wiring up the service selectors that I created both for the IP pool and also for the announcement layer would be fired up, right? So now if I do curl 30.0.10.1:8080, we can see our echo service. If I do that in the browser, same thing. Oh, :8080. Right, there we go. And then going back to the command line again, and we do that same -ss. Good. Hosting. So we can see our load balancing mechanism is still working. Right, we're still load balancing across two different endpoints, but this time we're coming in via this external IP address that's being announced via BGP. So this is a service type load balancer, and the service that I'm using here is type BGP. What are some other ways that we can express this load balancer inside of Kubernetes, which I think are pretty fascinating? So like another way that we could actually satisfy this load balancer inside of Cilium is like, I'm going to go ahead and delete that service that we created. Delete svc-echo lb, and then let's recreate it. You could also expose svc. So before I get ahead of myself, so what I've shown you so far is how to expose that service via load balancing. So let's go ahead and recreate that load balancing mechanism that we had. kubectl expose deployment echo type load balancer. name echo LB BGP labels. And you can actually even add in the exposed type, you can actually add labels right there. So I don't have to do that as an after fact. I can do that right here. Color equals red. We could all get STC. We see our two types, and we can see that we got that same IP address because it was just reused. So now let's do kubectl get service dash and echo LB dash OYAML. So here are the two services that we created, right? Here's one that is just the cluster IP. You can see it has a cluster IP address associated with it. And if we move down, you can see internal traffic policies defined, and it's set to cluster. And if we move down to the next one, to echo LB BGP, then we can see the same thing. It still has a cluster IP. And this is because we still want to be able to expose this service internally to other applications using that same internal load balancing mechanism. But we also want to expose it to external things, right? Which is where we set specified type load balancer, and where Cilium wires up a bit from that pool and announces it via BGP and makes it available to the outside world. That's how we get traffic into the cluster. Now, let's jump back into Cilium's agent real quick and take a look at how this actually works. I think it's pretty neat. kubectl exec CI dash cube system DS Cilium dash. So here is all of the configuration for our load balancer. Okay, so here is 30.0.10.0 or 30.0.10.1, and it's being sent basically to a generally available address where we want it to figure out where to send that traffic. There it is, sending that traffic specifically to 10.1.3.1.15. We're listening on that port. It's like we're listening on that node port 30559. So for example, just to show you how that would work, because we have a service of type node port there also, right? If I were to do curl, it'll get nodes dash OY. If I go ahead and curl 10.0.2.2 colon 30559. And that should route back to, I'm not sure if I have that turned on as a feature at the moment. Oh, sorry, it's not the 10 addresses, it's the 172 address. It's 172.18.0.8 30559. There we go. The nodes actually have two different IP addresses. They have an internal IP, and then the external IP didn't register. So the other IP address for that node, if I were to do kubectl describe node lab control plane, it actually has two addresses. The 10 those addresses enumerated. There's the internal IP. Yeah, it doesn't actually register it there. So there's node. Register it there either. Interesting. Well, they have a 172 address. That's actually the one that is being bound by Cilium here. So the node port actually also works. It's another type of load balancing. So just like the same way that we were talking about, if I do the same command and I grep for host name, we can still see that we're, well, in this case, we can still see that we're load balancing across two different endpoints. Now, why is it within Kubernetes that when I define a service of type load balancer, I get a node port? Like what's actually happening there from the mapping? And this is an interesting point because this is kind of one of those deep dive points that actually really highlights a key difference between what we're doing here with Cilium and what might happen inside of a cloud environment. So in a cloud environment, when you create a service of type load balancer like in AWS, right? You create that service of type load balancer, and the service of type load balancer will actually use the nodes themselves as the target and the node port as the destination for traffic that's being sent. It'll still terminate on the outside with whatever IP address you actually wanted to expose, like it might be, or sorry, on whatever port you want to expose. So the service of type load balancer will still expose port 8080 on that external VIP. But when that traffic is mapped back into the cluster, the traffic, typically the design pattern would be that the traffic would come in on port 8080 to a VIP. That traffic would then choose a bunch of backends on it and then send that backend traffic back to the nodes on the actual node port. And then once that traffic terminated on that node port, it would go up into the load balancing layer and determine from that particular node, where does it want to send that traffic? Does it want to send the traffic to a pod resident on that node, or does it want to send that traffic to a pod on another node? Okay. And again, if I just change this IP address, this is going to the actual pod there. So if I go to 330.1:8080, you can still see that we're balancing. So there are some other interesting things about load balancing, which I'm going to jump into here real quick and cover from the documentation perspective. We talked about cyber selectors, we talked about CIDRs and reserved IPs. We're going to talk about the L2 announcement here in a minute. We're not there yet, but we're going to talk about it. We're also going to talk about this feature here, where we can actually create a shared IP, like multiple services can use the same IP address. But we're going to get there in a minute. One of the other things we can do is we can actually express load balancers leveraging different IP protocols. So if you wanted to use like IPv4 and IPv6, you can do it, which is pretty neat. In my case, I've only got IPv4 pools that I've created, but if you wanted to create an IPv6, then you can actually go ahead and do that. You can also create different families. So like you could say prefer dual stack, prefer single stack, etc. If you have like a mixed mode cluster. Now, as of Kubernetes 124, we support multiple load balancers, and the way that they do that is leveraging kind of a similar trick to services of type ingress. Right? Ingress is another API within Kubernetes. I'm not going to jump into it in this conversation, but one of the big challenges that people ran into with ingress was they might have multiple types of ingress controller, or they might even have the same type of ingress controller, but they wanted to actually divert that traffic across multiple ingresses to be able to divide up things like bandwidth or throughput. In 124, we introduced the idea of a load balancer class to solve exactly that same problem. You might have different types of load balancer, and you might want to be able to specify the different type of load balancer class. Cilium supports by default, I should say, Cilium supports two different load balancer classes. So one of the classes is BGP control plane. In our configuration so far, that's the one we've been leveraging. We haven't specified which one to use, and by default, it will actually assume BGP as the as the class, but I could actually specify it as a different class. I could specify it as IO Cilium L2 announcer, and that would break the service that I had defined because there's no IP addresses associated with that particular one. Now, other things of interest, you can actually request IP addresses, like even multiple IP addresses associated with the same service. So we haven't actually explored that yet. But that's another way of actually understanding what's happening here. So let's take a look at that real quick from an example perspective. So this is a way of saying what configuration would be created for a given kubectl expose command. So let's go ahead and throw this into a file because what we want to do is add an annotation to it. So let's do the echo lb rec IP. And actually, let's go ahead and add our labels. I forgot to do that. Labels equals. So this is the thing that is created. You can see that label there. Labels color equals red. You can see the ports associated with it. You can see that it's a type load balancer and that the selector is app equals echo. All of that's in there. And in our documentation, we can see that all we need to do is actually specify this line in the annotations. So let's go ahead and copy that out. We'll throw that into our YAML. Now, we know that the CIDR for this is actually a different CIDR than the one that was described in the example. But let's say we want 100. To LB request. So I have my LB IPAM Cilium IPs 30.0.10 100. I have my color red. And so when I apply this, I should get 30.0.10 100. There we go. So we actually can also we can also request IP addresses that are associated with it, right? And I can still curl just like I would expect 0, 10, 100. And it works. All right. Now, there's another thing that they cover in the docs, which I think is actually pretty cool, which comes as something of a surprise, which is the sharing keys thing. Services can share the same IP or set of IP addresses with other services. This is done by setting libipam Cilium sharing key annotation on the service. Services can then have the same sharing key annotation, will share the same IP address or the same set of IP addresses. The sharing key is a string that can be any value. So that's a super interesting thing. So what if we create, let's go ahead and do that. Let's play with that because I think that's pretty neat. So let's do kubectl create deployment echo 2 image equals and then echo server port equals 880. It'll create service, actually expose, deployment, echo, type load balancer, labels color equals red. So I'm just going to expose the second service here. kubectl. Let's just do kubectl get SVC. So you can see the echo 2 service. Expose on the load balancer 3002. So if we do our curl command, we can see that the host name is echo 2. And if we go back to echo 1, we can see that the host name is echo. The difference between the two services. Let's go ahead and expose both services with a sharing key where they share the same load balancer. Well, let's check this out. So I'm going to go ahead and copy echo LB rec IP to echo LB share. So there one. And then let's go ahead and manufacture this. So we're going to do yank 18 down. We'll paste it. Nope. Okay, let's try that again. Yank 18 down. There we go. Paste it. Ah, there we go. All right. We have two services. We're going to get rid of this annotation. We're going to call this one share 2. Echo and echo 1, I think. All right. Describe service. Echo 2. Our selector is echo 2. Okay, so we have our selector for echo. We have our selector for echo 2. We're creating two different services of type load balancer. In our doc, we want to create this annotation. Let's go ahead and copy that over. This might be actually kind of an interesting race condition now that I think about it, because there won't be a service to share with yet. But one of them will win and get the IP address, and then the other one will share it, presumably. I don't know that you're supposed to create both of these at the same time. I would assume that you're probably supposed to create one and then the other. But let's see what happens. You know, it's Friday, and I'm excited. So there was our sharing key. There's our service echo LB share 1. It's going to be exposing selector app echo. And then we have echo LB sharing 2, which is exposing echo 2. They both have a sharing key. Let's see what happens. eCHO apply -f echo share. eCHO get SVC. Yeah. SVC. LB. So as you get services now, I see that echo LB share 1 is created using tree. And now if I kubectl apply -f, go LB share. How do I have to request the IP? Let's try doing that. Let's see if that actually helps. Okay, so I'm requesting an IP address across both services. It's the same IP address. I'm also specifying a sharing key. Let's see what happens. Well, that's interesting. So that's a difference. So we did get the actual IP address on share 1. We're not associating that IP address on share 2. Kubectl granted SVC echo LB share. The IP address 10. Oh, we're using the same port. Ah, is that true? Does that have to be? As long as oh, there we go. As long as services don't have conflicting ports, they will be allocated the same IP. That was my bad. Let's see. I love this program because it's very simple. What I don't remember is whether you can actually change the port that it listens on. Port and environmental port can be set to corresponding serial ports. Okay, good. Let's go back, try this again. Let's do kubectl delete -f. Go LB share. Delete deployment. Go. Delete SVC. Get all. Echo 2 is gone. We can create deployment echo 2. And then I can't set an environment with this command. Okay. All right, so let's do KubeCon create deployment. Echo 2 is equals admin. Go server or equals 80. And okay. And then let's go ahead and add our sorry, got distracted there. Containers, and then underneath our okay, so that should, according to the docs and everything else we see, create an echo 2 on port 8090. Let's go ahead and do that. eCHO. Apply dash F echo 2. What happened there? All right, KubeCon get odds. KubeCon. Okay, now we just edit our echo. Let's say KubeCon. Then echo LB share. Echo 2 will be 8090. So now this will use the same IP, but it'll use different ports, which is fine. Go ahead and do that. Control Y F. No longer conflicting. You can get SVC. You can see they both have the same IP. That works. Curl 30 0 10 99 colon 80. Posting. That's working. And 8090. Also working. Although there's only one pod. Yeah, it's only one pod on Echo 2. So shared IP addresses, different ports. Also pretty cool. What else? What else? What else we want to cover? Oh, service and subtype L2. Let's do that next. And then I think we're probably going to wrap it. So KubeCon get L2 announcement policies. I don't have any currently created. But here is an example of one that can be created. So in my case, I'm going to say, I'm going to go ahead and use the Cilium L2 announce policy. I'm matching on labels type equals L2. That's for the pod, that's for the service selector. And on the node selector, I'm matching on anything that isn't a control plane. I'm actually also specifying that I want interfaces to be each 0, and I want the load balancer IP addresses to be announced. Now, because this is an L2 announcement policy, I need a different pool as well. So I need a pool that is compatible with the IP space that the nodes are in. So in my case, I'm going to use the 172.18.100 network, because if I do Docker network ls find or inspect find, you can see the IP addresses that are associated with like the lab control plane 172.18, and the whole CIDR is the 172.18.00 CIDR, but there won't be anybody using the 200 range there, right? So I'm going to go ahead and use that for my load balancing. So I'm actually specifying that same service selector mechanism, just like we described before, right? So I'm creating a service of type, I'm creating a CIDR 172.18.100.0/24. That'll make it so that when I announce out over ARC, things will just work because I'm in the same network as the nodes themselves. And then I'm also specifying that the services that I want to use for this only match this value set, type equals L2. Otherwise, don't announce them via L2, because I don't want to announce all of my services on BGP and L2. I want to be specific about which way I announce them, right? And my BGP side is all set up that way so I can be specific. So that's, I just want to make sure that I also make it so that my L2 side is configured that way. So let's create our pool. And let's create our L2 announcement. And then we can actually go ahead and create a service that exposes it in that way, right? So if we do kubectl expose, deployment echo, and then we will do type load balancer, because it's still a type load balancer. And then we will do labels, type equals L2, and we'll do name echo L2. So this will make yet another service of type load balancer. But in this case, my labels are type L2 because I want to use the layer 2 mechanism to announce this. Get SBC, and you can see that IP address wise, I got a different IP than I did before, right? So I'm still using Echo, I'm still using the same backend. I still got a cluster IP, but this time I got 172.18.100.0 as my IP. Let's try curling that. 172.18.100.0 colon 80, and it works. Right? My source is 172.18.100.0. Now, what's interesting about L2 is that if I were to do kubectl get leases, inside of my L2 announcement, I can actually see the lease associated with the Echo server is on LabWorker 2. And that's interesting because it means, like, this is the interesting thing about L2, is that we're only ever going to announce that IP address out of one node because it's ARP, and you can only do that out of one node. Which is a challenge, because like if LabWorker 2 were to go away, then it would go away. And any load balancing actually requires that I move through LabWorker 2 to get there, right? So, for example, the requesting IP address will change. So let's do that. Let's do get Yeah, it's always coming out that same IP, right? So it's going to be that. It's going to be that one node every time. The requesting IP. All right. Where's that host I want to see? Yeah, well, it's the same. Okay. So that shows the L2 announcement side. We talked about the BGP announcement side. We talked about the L2 announcement side. We talked about how they're wired up in Cilium's BPF map. We talked about troubleshooting them. The only thing that's left, but it's actually kind of getting a little bit later in the day, so I'm not sure if I want to jump into this. This may be a thing for another time, but in the load balancer configuration, there is also services. So we also have the external traffic policy, which is really useful to understand how that works. But I don't know if I have enough time to get into it today. There we go. So external traffic policy. Let's talk about this real quick. So we talked about load balancer class. Let's actually just talk about it, and I'm not going to jump into it too far. But external traffic policy, by default, is cluster, and BGP control plane unconditionally advertises the ingress IP addresses of the selected service, which means that when that service has external traffic policy clustered, all of the nodes that peer are going to announce that service. But when the service has external traffic policy local, then BGP has to keep track of the endpoints for the service and only announce when the service has actually got a local endpoint, which is super neat. And I guess I have enough time to show it. So let's do that. So this is on the BGP side, not the ARP side. We talked about the ARP side. There's no like clever stuff. On ARP, it's actually just going to send it to the node that is announcing that one IP. But on BGP, we could be announcing 30.0.0 from lots of places. Make show bit. Show make show bit. Oh, Cilium BGP routes. Okay, that's probably an easier way to see it. So at the moment, we can see that all of the things are announcing 3099 or 1099. Actually, let's do this. It'll expose. It'll get pod -o wide -l app equals echo. So right now I have a pod on LabWorker and LabWorker 3 for the echo service. But you can see that I'm announcing on all 4 of my nodes. Doesn't matter. I'm actually sending all of that traffic to all 4 nodes. I'm attracting that traffic leveraging BGP to all 4 nodes with the intent that when it arrives, I'll still be able to send that traffic to that pod regardless of what node it shows up on. But what if edit service echo LB BGP? But what if we made it so that that thing that we're announcing on 30.0.10.1 was only being announced locally? What? Okay, there we go. That was weird. Okay, so now we see local, and that's there. And now if I go back to that same command, Cilium BGP routes, and I'm looking for 30, 0, and 1, if I just correct minus C, 30, 0, 10, 1. Yeah, all right. So BGP. So what I can see is now lab worker is announcing 30, 0, 10, 1. Lab worker 2 is not, nor is control plane, but lab worker 3 is. Right? Because I have local, which means that I'm only going to send traffic where nodes have a pod resident, which is pretty cool. And the reason that's important is because source IP address, right? If the source IP address has to bounce through another node, then that source IP address is going to change. But if the source IP address doesn't, it is kept so that it terminates on a node where the backend is actually resident, then it will always show. So let's actually just try that out real quick. Curl -ss 10, 30, 0, 10, 1, colon, 80, 80. Crap, actually. And we can see we're coming from requesting IP is 172.20.11. So it's always going to be the same requesting IP. But what if we go ahead and edit SVC, echo Duffie BGP, and change that to cluster. I don't understand that assertion failure. I have to figure that out. You can see the source addresses change depending on if we actually terminate to one of the nodes that actually has that service or not. That's the benefit of having cluster local, is that the source address doesn't change. All right, I think that covers everything I wanted to cover. I really hope that that was interesting. I know there's a lot of information in this episode, and I really hope that it's not overwhelming. I feel like it's actually a pretty cool topic, and there's lots of really good stuff. In the meantime, I will say thank you very much. I hope you have the best weekend of your life. I am going camping this weekend in the beautiful Marin Hills with my fam and a bunch of other friends. And so I'm really super looking forward to that. And I hope that you are out there having the best time of your life. And I will see you all next time in the next episode. I think I'll probably end up doing an interview with like one of my Cisco cohorts here, Marcos, not Marcos, Errol, who is one of the amazing folks here at Cisco, going to talk to us a little bit about how eBPF is being used inside of Hypershield. So looking forward to that episode. That may be the next one in about 2 weeks. In the meantime, you have a great time. If you're at RSA, look for me. I'll be wearing a black hat. Definitely come by and say hello if you're there. and I'll see you all next time. All right. Bye.